Hi, welcome to the Signal Path. I've got another repair video for you guys today. I know that you enjoy the repair videos, so I went ahead and I bought two broken power supplies from eBay. Both of these are non-functional. I bought them as is for, not too expensive actually, certainly worth much more than if they were working. And the bottom one is an Agilent E3642A. It's a single output power supply that goes from 0 to 8 volts and can give you up to 5 amps under that setting. And then you can also go from 0 to 20 volts and it can give you 2.5 amps. So it's a 50 watt power supply. It has a very typical interface which you've seen. I own a whole bunch of different Agilent power supplies. So it has exactly the same interface and button configuration and the same type of vacuum fluorescent display with this optical or electrical decoder in the front, and it's pretty good. These are very nice power supplies, very precise, very low noise. The one thing I don't like about the 3642A is that it doesn't have the ground reference at the output. It just has the isolated plus and minus at the output here, but nonetheless they're low profile because there's only one output, so they're very good for laboratory use. And the one at the top is an Agilent E3620A. This is a dual output power supply, 0 to 25 volts and 0 to 1 amps. And these are also pretty nice. These are cheaper and a little bit older, this one I believe. But it has independent voltage adjustments. You cannot set this to have a specific current limit, that it will limit at 1 amp no matter what, and it has a ground reference and two independent outputs, so it's pretty good. This has the buttons that switches the meter that to show whether on the first one or the second output, and you can see these buttons are already broken and one of them is missing. It's a very common problem with these things. You can buy replacement buttons fairly easily online, and if I can fix this, I will definitely think about doing that. And this one is already broken and coming off, so none of them work. They exhibit different problems, and I haven't actually done anything on them yet. I just received them, so I thought we'd get started with the more interesting one, which is the one at the bottom, and then if we have enough time we'll move to the top one at the top also. So they have, I think actually they have different problems. So let's go ahead and plug the bottom one, turn it on, and see what symptom we have, and then we can go from there. Alright, I've gone ahead and plugged the E3642A, so let's go ahead and turn it on and see what happens. Here we go. Well, there's a couple of things we observed. First of all, it beeped twice, and it's showing these random, really strange, but I don't think there are actually any characters, but that this displays an alphanumeric vacuum fluorescent display, so it can display characters as well as numbers, and it looks like a bunch of them are all almost completely on. And there's another interesting thing that I noticed, is that the brightness is not uniform across it. So I don't know if that's because the VFD itself is damaged or aged in a certain way. Some of those may have been on for longer than the other ones, so they become dimmer and darker. As you know, these VFD displays do age that way. But I don't know, every time I turn it on it seems like it does exactly the same thing. I can hear the fan turn on inside, and you hear it again, it just beeped twice, and none of the buttons does absolutely anything. Nothing. But I do know one thing. I know that if you hold on one of these buttons, hold on to it when you turn it on, you can put it into self-test mode. So I'm curious to see what will happen if I do that. So let me go ahead and let's see, hold, let's say this button on, and then turn it on. Oh, it beeped the third time. So it certainly did something internally. So these buttons are actually connected to the inside, but of course when I push them nothing happens, although holding one of them did make a difference. That is interesting. Turning this doesn't seem to do anything. Well, this seems to be completely dead. Well, let's open it up, let's take a look inside and see what's going on, and then if we can find out what's wrong with it. The fan is running and then this comes on, so there's definitely some power, and this is a hard power, by the way. This sounds like it disconnects the power directly from the unit, so it's not a soft power on switch. Well, there's only one thing we can do. We have to take it apart, see what's going on. Alright, this assembly is really easy. The back panel just comes off with 2 screws. These things typically have the rubber band that goes around them, or the little plastic piece that goes around it, which this was missing. It also has a handle that was missing, which is a shame, but I think you can pick those up fairly cheap as well. So let's go ahead and remove this thing. I actually haven't really seen inside one of these units before. I've seen the from my other Agilent power supply repairs, obviously I've seen similar models, but not particularly this one. Aha! Here we go, look at that. It's actually, the construction of this is rather different than the other power supplies now that I'm looking at it, and there's a couple of interesting things to note here, so let's go over those. First of all, obviously this is the heat sink where the main power regulator transistor are on it, and I believe that the main rectifier must be also on this as well, although I do not see it from the angle I'm standing. It might be on the other side, but I can see a bunch of MOSFET transistors here, which are surely part of the overall regulation. And then you can see that the main transformer is placed toward the front of the unit, and I guess they've done this in order to be able to put the heatsink here. I guess they could have also done the power this way, but then the airflow would have had to be in this direction. In this way, you can really get airflow back toward the back of the unit, which is usually free and not obstructed. This also helps the weight of the unit to be rather balanced, so it doesn't become really back heavy. So I think it's a smart choice to put this here. You can see a lot of wires going in and out of the transformer, and that's because this transformer has multiple taps and multiple turn ratios to give you different voltages going into the main power supply. Obviously, all of the main powers going into the power supply come from in this direction, and they go out of that direction. And what is interesting to note is that the main power lines going into the unit are not shrink wrapped, they're actually exposed, although they do have very nice soldered and washer screwed to the chassis, the earth ground. And you can see there's two earth ground connections here, one of them going to the main line from the outside and the other one going to the PCB at the bottom, and they're both connected to the chassis. There is also another earth reference, which if I'm not mistaken, I think actually goes to the display, which is kind of interesting. They're really making sure that they ground the display really well, because the display is connected to the body via only this piece of plastic, so there's really no good electrical contact to the display, and this is their way of making sure that the front panel is also sitting at earth ground. And you can see here that there is three main points in which the transformer is connected to the PCB. I believe that this is the output of the transformer, and you can see the main lines going through here through the transformer. There's multiple of them because this thing actually has a configuration switch to set it to 220 volt, 120 volt, 110 and 115 and so on. So as a result, it has multiple wires going into the transformer, and depending on the voltage, then you engage a particular turn ratio between the primary and the secondary of the transformer, and that's why there's so many lines. And you can see that the main lines go in here onto the PCB, and I believe that the front switch must be connected somewhere underneath here. You can hear it clicking, and that's how it connects and disconnects the main. The main is not connected right now. You may not see it in the camera, but that's why I'm bringing my finger so close to it. Otherwise, you got to be very careful. This is live here. Nowadays, if you get a power supply, these will surely have to be shrink tubed and carefully closed up. Otherwise, you would not pass. Now, a couple of things I see that is a little bit surprising to me. For example, look at this. You see that? You see that shaking around? These things are not glued down in any way. They're not, I cannot see any glue, any silicone glue, nothing on these. I'm very surprised. I would have thought that something that Agilent made would have had a better way of connecting these to the power supply, but no, they're floating. Well, floating, I mean, they're only soldered by their main pins. I can see that there is a couple of capacitors here which are all kind of zip tied together. So I guess they can all break together. They're all zip tied together. Again, this is free. You can see, look at that. I'm not putting too much force on this, huh? Look, I'm disappointed on this. I don't know why they haven't properly tied these things down. But anyhow, other than that, obviously the layout and everything else is very nice and very clean, to be expected from Keysight or from Agilent. Here's some power resistors there, perhaps for some shunt current monitoring. These are the main capacitors on the output line, and you can see big thick traces that connect the main transformer to this. So I would suspect that this line here on this side, let me peek on that side. Yeah, there you go. Yeah, just like I said before, the main rectifiers as right behind here. I'll flip this around so you can see it. And then these are the main output capacitors. Now these capacitors are Nichicon brand, so they are a very good brand. But I am surprised again that they're only 85 degrees C rated. They're not 110 degrees C rated. Oh well, that's another thing that's a little bit surprising. But anyhow, it's not too bad. There's a lot of dust here in this part. I guess it's because it's been running for so long. This unit also has, let me briefly lift this up. At the back, it has GPIB as well as RS-232, so you can communicate and control it via these two terminals, but it does not have USB. It's too old for that. And it does have the sense ports at the output, and also have levels at the output, the main terminal, so you can essentially take the output from here, but the sense is tied back, you can see. So if you really want to, you can bring the sense forward and then do IR drop compensation, as you know. So let me turn this the other way around. Here you go. Now you can have a look on this side as well. Like I said, here's the the main rectifier. Here are the main MOS, and some more MOSFETs, I believe, for regulation. And here directly underneath, in here, you can see, wow, there's a lot of dust in here. There we go. Get some of this dust out of here. There's a switch here, and there's another switch right behind here, which you cannot see very well. By the combination of these two switches, you can set the voltage, whichever one you want. And here's another closer view, 2000 microfarad capacitors right here, which are the good brand, but only 85 degrees Celsius. There you go. So that's like an overview of it. And then there's a bunch of other components, obviously, which I can quickly tell you a little bit about. So here's the main buzzer. We got two ICs here. I cannot really see the part number from here, but you can see that whatever circuitry is in here is in charge of the GPIB as well as the RS-232. Here's the RS-232 level converter right there. Here's some main processor for controlling the main functionality of the unit. I'm not sure if that's very interesting or not, but here's the main firmware IC, and this one says it has revision 1.5. I don't know if there is a newer revision or if this is even upgradable. The firmware is upgradable through perhaps the GPIB or not. I haven't looked. But I did check is that the service manual for this does not have the schematic in it. So we're out of luck there. We'll have to figure this out ourselves this time. There is no schematic. There has to be some reverse engineering. Here's the cable where all the transformers come into the unit, so we could potentially measure this. I doubt that there is any problem here, because if there was, then we wouldn't get any. If the fan and everything else is running, the display partially turns on, so it's not from that. But what I'm going to do is I always connect and disconnect it, the connectors, just to make sure if there is any oxidization on it. Perhaps it could be a reason for failure. Here's the main connector to the display. Now you can see that there's a lot of wires going to the display, and the display of course has all those buttons as well as the VFD and the control and the decoder and everything there. So I'm sure that the display has its own circuitry inside it which does these tasks, and everything else is rather nicely done. If I were to flip it over, let's see if there is anything at the back. Oh, here we go. Oh, let me put this down here. The back is rather bare, and there's not that many components on it, but it does have a botch. A little botch fix here they've done. There we go. Look at that. They've taken, there's some component in here. I don't know what it could be. It could be a resistor or a diode by the shape of it. I think it's a diode, and it's taken from here and then kind of botched there. But you can see that they've gone through the trouble making sure that it's nicely covered, and it's got, if they've gone through adding this, why didn't they add this type of silicone glue to the capacitors? I don't know. They should have. But you can see nice big traces. Here's our, oh, you cannot see, sorry, let me fix that for you. There we go. You can see very nice big traces here where the main current goes to the two terminals. Here's the first terminal, here's the second terminal. You can see this is exposed. I'm always outside the camera. Here we go. Let me see. There it is. Sorry about that. There we go. So here is a nice big traces. You can see that goes to the main two terminals. Here's one. Here's another one. Here's some current shunt resistors and so on to measure perhaps the current and monitor it. Although I'm sorry, I could be wrong. This is something else. This is a protection circuits, I believe. Yeah, these are resistors. Never mind. My mistake. These are not the shunt current resistors. So there we go. Fairly nice and clean. Looks good. There's a whole bunch of rectifiers on this besides the main rectifier. So we can go ahead and poke around it and measure around it and see what else we can find. But other than that, it's fairly straightforward. A whole bunch of different could be transistors or regulators. I believe there's a regulator. That's certainly a regulator. So looks good. Everything else good. So let me go ahead and plug it back in, and we can poke around a little bit, see if we have any ideas. Unfortunately, like I said, there is no schematic, so we have to find another way of debugging it. Now there's only two boards. There's the main board, which is this one, and the board that's connected to the display. There is really nothing else. So we have to break it apart and find out what is not working. So in the entire service manual, they only speak about measuring 3 voltages on the whole power supply, 3 or 4 of them. And that's the only part that actually is involved in debugging this in terms of finding a problem with it. Everything else is not included. So which is a shame, because everything else actually relies on the display showing you an error message, and then you can say that, oh, send it back to the repair center. That's basically what they're saying. But unfortunately, since the display is not showing us anything, we cannot use that. So let me just go ahead and measure the couple of voltages they're suggesting that we should be seeing. One other thing to note here is that because the display is not working, that doesn't necessarily mean the processor is not working, because we do hear the beep, we kind of do hear it trying to boot. So we'll have to find another way of investigating that. But I'm going to use my new Agilent STM3055A to measure a couple of these voltages. And like I said, I'm evaluating it, so I'm using it for different projects here. So let's go ahead and one of the main measurement points is this IC U110, which is actually a 5-volt regulator with a shutdown, with a delay and reset options built into it. And if there isn't any time, I'll show you the block diagram of that. So we are expecting to see about 5 volts and 10 volts out of that. And if those two are present, then the digital power supply section is present, which is an important measurement. So all I'm going to do is I'm going to go ahead and essentially probe this. Be very careful not to rest your hand on this. One side of this is live, so you know we're gonna go measure this point and this point, and I'm gonna give you a view of the meter so you can see what I'm looking at. There we go. So right now I'm not connecting it, so I'll tell you what I'm connecting. So I'm on pin number 3, and I should see V in of the regulator about 10 volts. Let's see what we see. There we go. There you go, 9.45, not too bad. That's about 5 volts. That's about 10 volts, I mean. And if I go here to the output, and this should be 5 volts, perfect. It's 5.029, that's perfect. Although this should have been 10 volts. By the way, it's a little low, but oh well, I think it might be okay. So that regulator is working, so all the digital circuitry is definitely receiving signals. That's not a problem. So let me go ahead and turn it off and flip it over. Like so, because the other voltages are all on the inside of this. So I'm expecting to see the plus and minus 15 volt supply as well. So I'm going to go ahead and try that. They're on some really small components, some really small diodes here. You can see, if you look carefully, you can even see that they have made those couple of points of measurements with pads available next to them. So here's one pad, here's another pad, and here's another pad. So those 3 voltages are exposed, and I'm going to use the these capacitors here next to it as a ground reference, one of the bodies of these guys. So let's go ahead and see what happens. I'm going to turn it back on, and once again I'm going to give you the view of the meter like so. So we're expecting to see the different voltages, the plus and minus 15 volts. So here's the first one, plus 12, is that the right one am I looking at? That's 38, that's the main voltage going into from the rectifier. Yep, so there is our first one, 12.8, seems like a little low, should have been. Here's minus 15, and so minus 15 is working. And this seems like it's a little bit lower than it should be, but otherwise I think everything else looks good. Yeah, minus 5 is there. So I don't think this has really a problem with the power supply. I'm a little bit worried about the 13 volts, but what I'm concerned about is that there's something that's shorted and broken inside that's pulling the supply down. But it looks like at least the power supplies are reasonably close to where they are supposed to be. So, you know, while I was doing that, I thought of something. There's a trick we may be able to play. This thing does have RS-232 and GPIB. We can see, maybe we can communicate with it through its GPIB port, even though the display is not showing anything. That will tell us a lot of information, because it will tell us if the main processor on the main unit is actually functional. If I can get any life out of this from the GPIB port, that would be a huge help. And then even better would be if maybe we can send a command to it and see if it does anything at all. By the way, I've measured the output voltage. It's just nothing there. I know that you guys might have thought about that. I did in fact try to connect something in here and see the voltage. It just is 0 volts. So that's not working. So let me go ahead and connect it up. I believe I do have exactly what we need. If I can get it out. Here we go. We need one of these guys. This is one of the Agilent. It's an E3642A, which I picked up long time ago from eBay. So we can use that to connect it to the GPIB port, connect this to the USB port, and open something like BenchView and see if we can communicate with it. So let me set it up. I'll connect it to the multimeter and then see what we see. So I was about to connect something to the GPIB port, and look what I just noticed. Look. This may seem like it's working on this unit, but it's not. It's not missing any of its components. These screws are not tied down to the chassis. They're only tied down to the connector. So if you connect something to it, it is free to do this. I don't understand how Agilent could have released something like this. I'm surprised that they would allow this connector to be loose. I mean, surely this will eventually break with especially because GPIB connectors are so large and they can put so much torque and so much pressure on these connectors. I think this is how it's supposed to be, but if you have one of these at home, you know, and try, let me know through the comment section if this is normal. But anyhow, this power supply is all about things not being tied down. Anyhow, let me go ahead and connect this up to the computer, and I'm also going to connect the output to a load and to a multimeter just in case. You know, I'm being very ambitious, but anyhow, let's try it out and see what happens. Okay, so all I've done is that I have connected in series with the output a 10 ohm resistor where the current, I can measure the current through the 10 ohm resistor using my Rigol DM30, I keep forgetting the model numbers of all these things, the DM3068, which is a 6.5 digit meter. So here I've set it to measure the current through a 10 ohm resistor, so that will be responsible for measuring our current. At the same time, I'm in parallel measuring the voltage directly across the output ports, and you know, technically this should be the other way around, but this doesn't support being cascaded on that side, so that's why I put it here. Anyhow, and that goes on to the Agilent DM3042A. So I can measure the voltage coming out of the supply here, and I can measure the current coming out of the supply here, and at the same time I have it connected to the GPIB interface right now, and the GPIB light is green because it's connected to the USB, but the unit is powered off. And what I'm going to do is I'm going to use the computer to look at, I'm going to open the Keysight Connection Expert, which is the old Agilent I/O, and then from that we can go ahead and see if we can get any connection to the instrument. So here you go, let's go here. What do we have here? There we go. So there it is, there's our Agilent I/O, and you can see that right now on the Keysight Connection Expert I have the DM3068 and the STM3055, and those are the two units from Rigol and from Agilent. So they're there, of course, because they're connected. Everything in my lab is always connected to the computer, so as you turn them on, they appear. So I'm going to go ahead and connect this on, turn this on, and let's do it. You can hear it being turned on. Let's do a scan here. Let's see if it... Oh, I just heard it made an extra beep. Look at that! There it is! Oh my god, it shows up! It shows up, there it is, the E3642A, Agilent Technologies. It tells you it's a 50-watt power supply, like we said, and it's on address 16. Well, that's a huge thing. So let's go ahead and minimize that. Let me go ahead and open bench view. As you may not know about this, I'm sure by now you know what bench view is, but anyhow, it's software from Keysight to communicate with everything. There we go, and look at that. It actually shows up at the bottom. Here it is, like this guy. You can double click on it, acquiring. Oh, I heard it beep again. That's amazing. There we go, this thing looks... Oh, look at that. Aha, very interesting. Look, it says, I don't know if you saw that or not, but just before, there you go, I can bring it back up. It says, look, it says instrument error cleared, 601, front panel does not respond. That is huge. This is actually telling us what's wrong. It's saying that the front panel, the display, did not communicate with the computer, which means that everything internally is working, but not the front panel. That is a very useful little thing. So let's go ahead and see if we can set it on and off. So right now you can see that it's saying that it's doing a live measurement, so it's actually doing the measurement. It's doing, let me do this. There you go, you can set all the settings. I really like this bench view. I wish every option was free, but of course it's not. But anyhow, so it's set to the 8 volt range and it's set to 0 volts. So let's go ahead and set it to something. Let's set it to 1 volt. 1 volt. Limit is 5 amp. It still is measuring 603 microvolt and 213 micrams, so there's nothing. How do I turn it on here? Oh, there we go. Here it is. Turn it on. It says, it's measuring. Oh my goodness, look at that. How is that for awesome? Here's the supply voltage, 0.9976. The computer is reporting 1 volt, which is very close. And it's supposed to be, it's supposed to be 100 milliamp, and it's 97.3. That is brilliant. So the supply is actually working. So let me set it to a different voltage. Let me set it to 10 volts. So I change the range so we can make sure the range works. And I'm setting it to 10 volts, and there we go, 9.998. You can see the fan just kicked up because it's consuming a lot more current, and this should say about 1 amp, and it does, and you can see that it's slowly rising up as the resistor is changing temperature. So it looks good. I can't believe it. So the supply is actually working, even though the display still showing that gibberish. So that is a huge discovery. So this communicating through the computer through the GPIB paid off. It allowed us to be able to debug it. So if I go back here, there we go. You can see that it is, setting 10 volts. It's reading the voltage and it's reading the current correctly as well, 977. The Rigol is reading 976, and this is 10.001, and the Siglent is reading 9.998. So it looks very good. Everything seems to be, and again, the Rigol, the Siglent is expected to read lower because there is an IR drop through the connectors in the front. So it actually is fully consistent with each other. And this, this BenchView software can do other things. You can plot for you and all that. We can look at that some other time. But this is great. So let's go ahead and take apart the display, take it out, take a close look at it, see what we can do with it. There we go. I removed the front panel, so you can take a little bit of a closer look on this side now. Oh man, this is heavy. Here we go. There, you can see now better the construction, and you can see the transformer is kind of almost sitting on top of, there's more protection circuitry there on top of a PCB. Here's the long plastic piece that connects to the power, and you can see the output terminals here with some extra protection circuitry right on there. So there you go. That's as far as that is concerned. So at least from our new measurements and the tests that we did, this part is fully functional. It seems to be working. I did some more measurements, voltage and currents and so on, and it's dead on. It doesn't even need to be calibrated. And so here we go. This is now the focus of our attention. So we have to disassemble this guy and figure out what's going on. So there's a whole bunch of circuitry in there. Obviously, because the instrument can tell that there is no communication coming from this, it means that there is a processor in there that handles some kind of serial or parallel interface to the main board, which does everything that needs to be done. So there you go. That's our problem. Let's go ahead and see how we can disassemble this. So if you take a look at this thing a little bit more carefully, you can see that there is a little notch here where the PCB is being cut out, so that this board actually cannot move left or right because this piece is blocking it. These two pieces of plastic are blocking each other. So if you were to bend that piece of PCB forward up, you can then slide this to the right. But it's not so straightforward as just as that. You can see that here these plastic pieces are holding it in place. So if I slide it to the right, then this piece of plastic will align with the hole in the PCB, and this should come off. But then on this side, we have the main knob. So this knob obviously has to come off. There we go. That was a little bit easier than I thought it would be. And then it should slide. But upon, if I look at it a little bit closer, you can see here that there is some kind of a screw underneath. So I'm not sure how that will work out. But there's something else that gives me a hint that the display has to come off first, because you can see that they have intentionally made these cuts much larger, and they would only do that if they were expecting you to be able to access the little latches on the front of the display in order to be able to take the display off. So I'm going to take one of the screwdrivers and I'm going to push it against that and see if I can get this panel off first. That will give us access to the screw, take the screw off, and then see if I can slide the supply out of this bracket. So I think I was on the right track, because I was able to easily use these the plastic latches here, which I didn't damage too much, I don't think, to take the panel off. So now, what do we have here? There we go. Here's our VFD. You can see the classic vacuum fluorescent display. And here's something, a couple of other cool things to look at here, is that you can see that underneath it, it has all the different voltages that this supports. Look, 8, 20, 35, and 60. And the 35 and 60 are on a similar model, which is configured differently in order for them to be able to go up to 60s. I think it's still only 50 watts, so then the current will go down. But I wonder if there is any modification that can be done to the PCB to enable this, and then the firmware will automatically detect that. You can see overboard protection 1 and so on are all here, the output 1, output 2, here's OVP 1, OVP 2, and so on, the calibration and limit and so on. So there's everything you would need to see on there. There we go, and I think I was right about this, because I don't believe that you can remove that panel without removing this. So let me put my screwdriver back in place, if I can remember where I took it from. There we go. And we should be able to easily take this off. There we go. I think I should have the right pair of pliers for any occasion. There we go. There you go. Should come off easily. There we go. There it is, and the washer as well. So now we should be able to. You can see that there is a little space for this to actually be able to slide to the left too. There we go. So now all I have to do is bend this guy, hopefully without breaking it. My camera is in the way. I'm trying to do too many things at the same time. There we go. I think I just did it. Aha! That should do it. There we go. That is awesome. There. So there's the buttons are left behind, obviously with the plastic conductive component at the top, and they just touch the PCB. You've seen this, I'm sure, many times. Here's a decoder. These are notorious for breaking down, by the way, in these models. So there it is. There's our display, and as we expected, there is a whole bunch of circuitry right underneath this display. I have no idea what those components are yet. Unfortunately, damn, the schematic's not available. It would have been made a lot easier to debug this if the schematic was there. But now, how do we access those? Now there is a metal bracket around here, and this metal bracket seems to be, although the display is loose, but I can't bend the display any higher than that because this metal bracket is in the way. And the bracket seems to be soldered to the board with these two joints, and there's one joint here and a couple more these ones. So there's 1, 2, 3, 4, and 5. So there's 5 places where the metal bracket touches the PCB, and we should be able to perhaps remove the metal bracket by desoldering it and then carefully bending the display, the vacuum fluorescent display, up in a 90-degree angle to have access to this. There's no pins on there. I think there's some pins here, but I have no idea what those are. So yeah, that's what I think I'm going to do. I'm going to go ahead and remove this bracket so we can bend this forward, hopefully without breaking the VFD. So there was a fight between me and the bracket, and I think the bracket lost. It was really difficult to remove this. I had to actually cut these pins really short because I believe this is assembled in one piece, so it doesn't really allow you to remove this without removing the display, but I managed to get it out because the display has quite a few pins and I didn't want to go ahead and start unsoldering all of that. So I took it apart basically, and I lifted the VFD off the board so we can take a look at the components. And to be honest, it didn't take very long for me to see that something has gone horribly wrong on this board. If you look closely, you might even be able to see it on camera. I'll try to zoom in. You see that? Right there on that IC, there's a bulge on that. It's most definitely has a spot where I can even easily feel it with my finger. So that's dead. And not only that, if you look at this IC here, you can see further sign of damage on it right there, that this is also dead. And so if you take a close look at it, and you can kind of start to guess what's going on here. Let me just tell you what components are on here, and then I'll do some measurements to further illustrate what I'm saying. So here, this is an LM339. This is a quad comparator IC. This is an Intel M8015, which is just a basic processor and has a whole bunch of IOs. Now, I don't see any programming ports on this, so I suspect that this actually gets programmed during power on. So hopefully replacing it would restore its functionality, although I'm not 100% sure. I don't see any other memory on this, and this is EEPROM based. This is an let's see if I can read the part number. This is an HC299, which is an 8-bit shift register IC, parallel shift register IC. This is a D flip-flop IC. This is an OR gate, area of OR gates. This is an VFD display driver, which is, we can do basically multiplexing, all that. It's a high voltage IC. And this is a 5-volt voltage regulator here. Now, let's go ahead and take a look at the power supply that powers this unit and powers this unit, because I know that this unit's maximum power supply rated is only for 5 volts, so you cannot put more than 5 volts on it. And then we can go ahead and take a look at the voltages on this. So I just did a few probing here. I'll do some more with you, but the voltages that come into this board are, besides the logic IO levels that go back to the main processor, which then communicates with this and detects its presence and so on, it also receives plus and minus 18 volts and plus and minus 12 volts. Most of it is because you want to be able to power the VFD, not that any of these components need it. There's also a few diodes and so on this board as well. So let's go ahead and plug this back in and do a couple of simple measurements, because we know what to expect from some of these components, like the power supply that should be on there, as well as the power supply from the regulator, so we can do a few basic measurements and see what we can find. Here we go. So I've plugged this back onto the main motherboard, and if I go ahead and turn on the power supply, we will hear the two beeps indicating that the display is not working. So let's go ahead and do that. Here we go. And you can see that the display shows the same characters it was showing before, which is the faulty characters. Now, under this condition, this IC is completely cold, and I suspect it's because whatever happened to it has happened already so much that it's completely dead. It essentially has no current going through it anymore. The IC is finished. And then on this side, this IC gets extremely hot. And so whatever has happened to this one, now it has a short in it or something that is causing a whole bunch of power to run through it. So one of the easiest things to measure is the 5-volt regulator. Now, I have this multimeter here, so we should be able to use the Fluke289. Sorry, I have too many things here on my way. There we go. So the ground node for this one is right here, and this is the pin on this side, which is pin number 8. It's supposed to be the input voltage, and pin number 1 is supposed to be the output voltage. Remember, this is a 5-volt regulator. So here's this input. We see 17 volts. It kind of makes sense to see 17 volts because it's one of the power supplies that's coming onto the board. Now let's look at the output of it. And on the output, what do we see? We see 36 volts. So not only is it not stepping the voltage down, somehow it's going to 36 volts. So something on this board has gone horribly wrong. And now it makes sense why everything is dead. Because now if I go ahead and measure the power supply of my Intel processor here, the little Intel microprocessor here, which we expect to be at maximum of 5 volts, and that's this pin 44, and I have a ground pin over here, and if I go ahead and measure its power supply, of course it's going to be sitting at 36 volts also. So this poor power supply, this poor processor that was supposed to have only 5 volts, at some point has received 36 volts, and obviously has completely died and blown out as a result of it. Whatever is happening to the VFD driver is something similar because it shares a 5-volt power supply. Now this one hasn't died, but you can imagine it's getting 36 volts somehow and it's dead. Now I'm not quite sure, to be honest, where or what has happened and it's causing the 36 volts to show up across everything. I mean, all these components here, except for the CR components, the diodes are on there, that the really small components, are easily recognizable. I don't know what this part is. Its part number is XBVF5, so I have no idea what that is. But anyhow, so what I'm going to do is I'm going to go ahead and see if I can get replacement parts for some of these and start removing these ICs, these two main ICs from here, and see if I can get a good power supply regulated first. And if by removing these guys I see a 5 volt and I replace that, then at least we know that maybe perhaps this was the problem when one of these guys died and shorted everything together, and then we can go and do a replacement. It looks like I won't be able to finish this right off the bat because I don't have any of these components available, and unfortunately this processor is really hard to get a hold of, and the only supplier that I see sells them for $33 a piece. It's quite expensive. So what I'm going to do is I'm going to remove them first and wait for replacing that, and if that works, then it'll be worthwhile buying that processor. So I went ahead and I removed the VFD controller IC here, and it wasn't that easy to remove it, but anyhow I was a little bit hasty, so one of the pads came off, but I'll have to repair that later. But what I do notice is that I think I found out exactly why this thing failed. So if you look here, these two pins on the side that are right next to each other, I'm surprised that these two pins are next to each other, because one of them is the VPP, which is the power line for the VFD driver, which can go all the way up to 90 volts. This IC supports up to 90 volts. But the pin next to it is the VDD, which is only 5 volts, which is the I/O voltage in order to drive serial data into the driver from the microcontroller. Now these two pins are next to each other, and some kind of failure inside the IC has caused these two pins to be shorted together, because when I was measuring it, if you remember, I measured 36 volts on the 5 volt regulator. That 36 volts is the difference between the ground and the VDD of the VPP voltage of this. So internally, the failure in the IC had caused these two pins to be shorted, and that short caused 36 volts to appear on the 5 volt line of the entire board. Unfortunately, that basically means that most likely everything on this board has died. The regulator is dead because without the IC, I measure 0 volts at the output of the regulator, but when I remove this, the 36 volt that we saw had disappeared. So at least removing this IC eliminated the short, meaning that the 5 volt rail is now open. It's not connected to 36 volts anymore. So this is definitely, in my opinion, the first point of failure. As soon as this failed, 36 volts showed up on the 5 volt regulator line, killed the regulator, kill the 8-bit shift register, the flip-flops, the OR gates, and I found out what this is. This is just a voltage reference monitor. If the voltage drops below 5 volts, this guy will automatically reset the VFD driver so that spurious and weird characters don't show up on the display. So this is most likely dead too. I looked at the specification for all of these ICs, and the maximum rating for all of them is no more than 7 volts. So having 36 volts on them most likely has killed them all. And I checked, the 5 volt is connected to all of these, and you saw that the processor is dead. The only component that has a higher supply voltage than everything else is the comparator, but unfortunately the comparator, I measured the input and output voltages of one of the comparators and it's inconsistent, so most likely that's also has died somehow. So I have gone ahead and ordered every one of these components. These are all very inexpensive. These are typical 74H series logic circuits, so they are very cheap, and the regulator is very cheap. So is the comparator. This was very difficult to find, and fortunately I only found one distributor, and they were selling them for $33 each. So I went ahead and I bought one of these, and now we'll have to go ahead and replace all of these components. My main concern is that some of these small diodes that are on here, which I could not really identify because I don't have the schematic, may also be dead, which I will not know until I basically replace all the components. But I'm going to go ahead and remove these one at a time, and then I've already ordered everything, so we'll wait until those things arrive and then replace them and see if it comes back to life. Here we go. I took everything off now, so it's almost a full reconstruction of this thing, and we're going to go ahead and replace them. And finally, all the components have arrived in the mail, including the processor, the Intel processor, and unfortunately I had to buy 5 of them because that was a minimum order. So this actually cost quite a bit, about $50 I think. So it's an expensive repair actually, and I don't even know if it will work considering how much reconstruction has to be done. But something else arrived in the mail, which really made my day. This little box came from Tektronix, and it's signed by a few of the employees at Tektronix that I know and I've spoken to, and they kindly assigned this and sent it to me for the end of the year. So I was really curious what's in here, and anyhow, so let me show you. And I thought it was pretty cool, and look at that, they are Tektronix MDO cookies, and they're actually quite delicious. And well, somebody, my girlfriend, snuck in there and ate one before I had a chance to make the recording, so she stole one of them. But they're really awesome. So now we got that Tektronix MDO cookies that we can eat. And I want to send a shout out to Tektronix and all the wonderful people who signed this and sent it to me. You guys made my day. This is pretty awesome. Anyhow, so let's go ahead back to this. So I will place the VFD in here and fix the little pad that was broken. Once we solder this in, I can power it on and make sure that there is no short and anything else, and then it looks good and the 5 volt is free. And then I will start populating at first, putting the regulator in, and then going through all the individual components. And before I do that, I just wanted to quickly also show you just one page of the data sheet for each of these components, so you just get a little quick idea of what goes on there. So there's more than just me replacing the components. Take a quick look and make a few comments about each of these components, and then we can start reconstructing it. So let's go ahead and start that. So let's start with this. This is the block diagram of the Intel processor, which is the ADC51BH. And you can see that this is a very straightforward classic processor architecture. It has 4 ports, which are memory mapped IOs, and these are the interfaces to the outside world. And you can actually program this through these IOs as well. And you can see the complete CPU bus inside it with all the different little components that goes into it, like the EEPROM. All the ports have latches on them, which makes sense because you have to latch these onto the bus depending on the execution cycle of the code. There's a program address register, some buffers, and the PC incrementer, which program counter, which increases and counts toward the individual lines to execute the code. Here's the main ALU in the center of the unit. This is a very basic processor, and it's a temporary register, so instructions are loaded into temporary registers and then computed by the ALU. and then send on to the memory mapped IOs, where they can interact with various things like the RAM and the timing control and the oscillator, which are here. So everything kind of ties in together. So it's a very, very simple, basic processor when you can follow the block diagram. You can usually learn about these things if you take computer architecture as an undergraduate degree, and then more and more advanced stuff later on. And I was looking for the interrupt handler here, which there should be somewhere. I just wanted to, there it is, right in the middle. So here's the interrupt serial port and other timer blocks, where you have to have an interrupt handling system for a processor and so on. So, you can learn about these at your own time. I thought it would be interesting to show you. So that's one of the components. Another component that I'm replacing is the LM139. Actually, the one that's on the board, I think, is LM339. Which is nothing more than a quad competitor, and you can see the block diagram of it in here. Very, very straightforward and simple. Here's the packages and SOI package and so on. A pretty SOIC package, I'm sorry. And then there it is. So this is what it is. Very basic. You can see some application circuits and so on for it, for a multi-vibrator, for example. And pretty straightforward. Nothing fancy going on there. Here's the little block diagram for the 74HC 299, which is nothing more than an 8-bit shift register. So you can see here there is an 8-bit shift register here where you can load data in serially, and then they can come out in parallel. What is interesting about this is that these the output buffers that drive out of the IC are tri-state. So that's one of the features of this IC, and you can see output enabled and output enabled bar 2 here control the different types of states that the output buffers can have. Pretty straightforward. Also, nothing fancy. You can see it supports different addresses, so you can have an array of these and address them individually and so on. Pretty straightforward and nice. There we go. The next thing that is on the board is a 74HC T74, which is a flip-flop. Just a bunch of flip-flops, and there's a dual edge-triggered flip-flop inside one IC, and you can see a block diagram of that. This is a CMOS flip-flop, of course, and it has clock and data and clear and preset, and it has Q and Q bar. Very, very basic flip-flop architecture. I'm sure that you've seen these before. Typically this is how something like this would be built if you were to synthesize it using RTL code and so on. So very cool. Let's go. The next thing is the MC74HC02A, which is nothing more than just 4 NOR gates. So nothing, I don't know what they're doing with it, and there I haven't really followed the pins around, but you can see, for example, the operating range from 2 to 6 volts, something like this. So obviously with 36 volts it's most likely dead, and it's nothing more than a bunch of NOR gates. The next thing is the 78L05 on this board, which is a 5-volt regulator. This thing comes in a whole bunch of different flavors depending on the XX at the end. Depending on the number, it's a different voltage regulator, and you can see this schematic of it here, where the output is taken from here. Here's our current monitoring port here, and there's a resistive divider to divide the voltage out, and goes back into a differential pair, and this differential pair steers the current left and right, where then it is controlled via a reference generator and so on to adjust the current. So this is like in a feedback network, of course, to set the output voltage to a fixed value, and here's the input voltage and here's the ground. So you can go ahead and analyze that. This is a fully bipolar implementation as well, and let's go ahead here, and this is the the last thing? No, there's one more thing after this. This is the under voltage sensing circuit, the MC34064, and this is a very, very simple circuit. It has a 1.2 volt reference internally and a comparator with hysteresis built into it, and there's a reset pin as an output. So you put an input voltage in there, the input voltage is compared with the comparator to the 1.2 volt reference, and if it's above and below that, then it will trigger this bipolar, which then is an open collector output that can be used to reset a microcontroller, to enable or disable something, to sense under voltage and so on. They use this to reset the VFD driver so that unwanted characters don't show up. Very, very straightforward and simple circuit. You can buy this and play with it. These are really, really cheap components, by the way. And here's the last thing, which is a 32-channel VFD display driver. This is the thing that I think has failed first, and it's really straightforward operation. Again, he has a 32-bit shift register with a data in and a clock and a data out, so you can cascade multiple of these, and then the data, once it's shifted in, can be latched, and then you can enable it, and that enable will then apply the output directly to the drivers, and these high voltage drivers operate from a VPP, which can go all the way up to
very high, 90 volts or so, even though so there is a VDD that sets these to a 5 volt IO interface, but the VPP here for these output inverters can go all the way up to 90, which provides a high voltage at the output, can drive the VFD components. Now, there's a strobe line here, which can of course strobe the inner output so that you can switch back and forth to different segments of the display and so on. So again, really nice and easy, straightforward. So now that we have seen all the data sheet for all the components, we can go ahead and replace them, starting with this one. All right, here's step one of the reconstruction. The VFD is back on the board. I've soldered it up. I think all the connections are made, and I fixed the broken pads. I didn't film it because I didn't think you guys want to watch that. So we can go ahead and measure from the ground up to the 36 volt supply, and it should still be there. There it is. Here's the 36 volts, and I can measure the pin right next to it, which was the 5 volt rail. And if I go ahead and measure that now, you can see that it's kind of sitting around of 0.5 volts or so. It's just floating. There's nothing driving it because the regulator is not there. So that looks good. Doesn't seem to be interfering with the 5 volt supply at the moment. That's promising. That's a good step. There's nothing showing up on the VFD, by the way. I just took a look at it and there's nothing there. So next step, let's put the regulator on, establish our 5 volt rail, and then continue populating the components. All right, and here's where the magic of television. Step number 2. Our 5 volt regulator is on, so I should be able to measure 5 volts from the supply of one of these ICs. Let's go ahead and touch that. And I don't remember which one of these was 5 volts. I think this should be. Oh, wait a second, maybe not. Let me figure out. I can actually measure directly on here, see if I see 5 volts. There it is. That's our 5 volt rail. Look at that, 5 volts, perfect. So now the VFD and the which actually gets quite warm. Wow. I hope that means it's still okay. Anyhow, the 5 volt regulator, and the VFD seem to coexist and seem to be working. So let's go ahead and do the next thing. I think I'm not going to do them one at a time anymore. I'll just install everything, including the processor. I think everything is okay now that the 5 volt rail is alive. I don't think we should run into any problems. And then we can go ahead and see what happens. Here we are. I've soldered everything on. And there's a good news and a bad news. The good news is that all the voltages are correct, and then now that I also have the microprocessor in there, I measured everything looks good. Even the microprocessor, which has a clock output, which is the 1/4 clock rate, is also working. So I think everything is pretty much functional. But here's the bad news. In my haste, I didn't pay close enough attention to the fact that the 80C51 series microcontrollers is a Mask ROM set of that microcontroller, not a flash-based one. It's very unfortunate because a Mask ROM microprocessor such as this one, the code that is essentially would be executed by the microcontroller is set at the time of manufacturing. That's why it's called a Mask ROM. It's done at the time of when the metallization in the microprocessor is made. So it cannot be changed and it cannot be overwritten. It's a permanent, which is very unfortunate because I don't even know what's on these then that I bought. But anyhow, I think that's unfortunate error on my part, but that's okay. There's two ways out of this. First of all, soldering this on here was important because I wanted to make sure that all the voltage and everything would still work, and it does, and doesn't seem to be causing any problems. So now I think is a good opportunity to turn to you guys and ask you if you happen to have a replacement Mask ROM, proper Mask ROM written version of this for this particular display, or if you have a display that's completely broken or the VFD is cracked or something like that we can salvage one of these from. The other opportunity is to replace this with one of the flash version, which is completely pin compatible, and if somebody has a code that would go into this, then we can try and downloading it and use it there. Everything works, but of course because this doesn't have the code in there, it won't communicate with the power supply. But I think if we were to change this, everything would work. So I'm sorry that I can't show you this working, but I'm fairly confident that this is would be a successful repair if you have to change this. So I think what I will do is I will turn to you guys and ask you if you have replacement, and then if I get one of these and find a solution, then I can make another episode where I also fix the other power supply that was at the beginning of this video. But I think it was an interesting learning experience nonetheless, seeing all the components and the data sheet and the replacement and debugging, still quite valuable. Nonetheless, let me know. I'll be very, very curious and eager to see if you guys have a solution for replacing this component. Well, thanks a lot then. Until next time.